Professor Vikraman Balaji, who was a student of Professor Seshadri, to say on the life and works of C.S. Seshadri. Now, yeah, Professor Balaji.
Thank you very much. It's a pleasure to be able to share my views on Seshadri's life and work. I thank the organizers of the conference for giving me this opportunity. So I begin with my first slide here. This is my first talk of this kind. So Seshadri was a mathematical luminary of post-independent India. He passed away on the 17th of July after ailing from deteriorating Parkinson's disease. He passed away in his home in Mandaveli, Chennai. He was with his family when this happened. That was last Friday. I dedicate this talk to his family, his son Giridhar, daughter-in-law Padma, grandsons Rangasai and Anant, and Seshadri Sundari's daughter helper over the years, Vadivu was her name, whose devotion to both of them was exemplary. So this talk is dedicated to them. So I begin with a little bit of his life and then quickly go into his mathematics. Seshadri was born on the 29th of February, 1932. He joined the Tata Institute School of Mathematics in 1953 after completing his bachelor's honors degree at Loyola College in Chennai. He did his PhD, finished his PhD thesis in 1957. Seshadri's doctoral thesis was entitled Generalized Multiplicative Meromorphic Functions on a Complex Analytic Manifold. And this thesis, apart from a few other things, gave an independent proof of the so-called Birkhoff-Grothendieck theorem on vector bundles on the projective line. Just to recall what this theorem was, historically, this was the result which looked at, considered holomorphic vector bundles, at least that's what Birkhoff did, holomorphic vector bundles on the projective line, and it was proved that it was a direct sum of line bundles up to some canonical equivalences, identifications. So this was the main theorem, but the theorem historically, Grothendieck proved this not just for vector bundles, but for arbitrary principal bundles. Well, the result on vector bundles actually goes back to Dedekind and Weber in their famous paper of 1882. And there is a very nice historical outline in this. I've given this link here to Charlot's article, which tells you exactly the various people who worked on this and how one can actually go back to Dedekind and Weber for the vector bundle case. So this was Seshadri's start of his journey. Seshadri came to Paris in 1957, and there is some sort of apocryphal story about how he is supposed to have met Serre in his office. Serre had actually posed the following problem: over n-dimensional affine space, are there non-trivial vector bundles? In other words, is the following statement true? Is any projective Noetherian module over the polynomial ring K(T1, T2, Tn), where K is the field, free? Is a projective module, finitely generated projective module, free? That was the question. For n equal to 1, the ring Kt is an integral principal ideal ring. Therefore, any Noetherian torsion-free Kt module, in particular any projective Noetherian module, is free. One could see, for example, Lang's algebra for all these things. For n equal to 2, it was already a very difficult question, and Serre had, it was a conjecture of Serre's that, in fact, it must be true, or at least this was a question. I would call it a problem. It was not a conjecture. So, and here, for n equal to 2, the fact is that there are no non-trivial bundles either. And this is the theorem due to Seshadri. This was very early in his entry into the Paris School of Algebraic Geometry in 1957-58. And it kind of shot Seshadri immediately to stardom because, it was a kind of a unique argument. It was a beautiful argument there. The final affirmative answer in all dimensions, that is, any projective Noetherian KT1, T2, Tn module is free, is the theorem due to André Suslin and Quillen, which was done independently by them sometime in the 1970s. So one of Seshadri's, I think Seshadri's first PhD student, Pauman Murthy, carried on from Seshadri on this and proved the theorem for n equal to 3 first, and then did a lot of work in collaboration with Hyman Bass in those days, which was the foundation for this whole theory. It just grown into a huge, structure in commutative algebra and algebraic geometry. Okay, so when Seshadri reached, or when he landed in Paris at that time, and there is the time that he finished his doctoral work, algebraic geometry itself was undergoing a unique revolution in the hands of Alexander Grothendieck. The previous generation of Zariski and André Wei's work, was there as a huge body of work, and many people had worked in it, but Grothendieck was revolutionizing the whole subject. Seshadri went to Paris in 1957 and very quickly entered the sanctum of this new temple of algebraic geometry. And the very fact that he could enter the temple into its sanctum provided him a very distinctively unifying perspective. Whoever entered the temple in those days got this perspective, which connected it to all branches of mathematics at some level. This kind of universal perspective was Grothendieck's view in some sense. André Weil had published striking conjectures linking number theory to topology, two very distinct branches of mathematics. And this was one of the driving forces behind the Renaissance in algebraic geometry in the hands of Serre, Grothendieck, and several others in Paris. And it was a heady time, I believe. Seshadri has told me several times that it was one of the most exciting times. Developments were taking place almost on a daily basis, and there were these big seminars going on. There was a Cartan seminar, there was a Chevalier seminar, and talks given in these seminars were on recent, very, very new developments in those days. And Seshadri gave 3 talks in the Chevalier seminar, one on Picard varieties and their compactifications, and one on Cartier operations, both of which are very well known. The one on Picard varieties was later written as a paper by him. And this work on Picard varieties was in some sense kind of a precursor to many of his later works on vector bundles, on smooth varieties and singular varieties. And much of his later work had some sort of you can trace it back to his early ideas. In fact, his thesis itself was on vector bundles. So I guess all his later works were somehow connected to this. I directly go to the Narsiman-Seshadri theorem. In between this period, I think in early 60s, Seshadri also gave a different proof of the so-called Weisenbach Theorem. Very distinctively original proof of the Weisenbach Theorem, which interestingly, he didn't pursue that kind of the whole theory there, but it was taken up and developed a lot by Grosshans, I believe, and there's a whole concept called Seshadri's sections, which comes out of this work of Seshadri's. I don't want to get too much into the details there because it's a general talk, but Seshadri had whatever he touched was non-trivial, and that was his style, and that was perhaps his keenness of his intellect. So the Narsiman-Seshadri theorem, it came in 2 papers. One was in Math Annalen, and the second one was in the Annals of Mathematics. So this work had its roots in the work of André Weil on generalization of abelian functions, which was written sometime in 1938. I think that was. And its foundations were very closely linked to the work of Poincaré on the so-called uniformization theorem. This perspective of connecting it to the uniformization theorem, I'll indicate a little soon enough now, but this perspective comes from today's vantage position. I don't think either Seshadri or Narsiman had any such perspective at that time, but it was Narsiman who told me about this links or sort of mysterious unconscious links to a certain approach to the uniformization theorem. I'll come back to that later. But the roots of this work really were in Wales' paper on the generalization of abelian functions. So what is the Narsiman-Seshadri theorem? So this theorem is a prototype of some sort of a theorem on correspondence, the equivalence of categories kind of question, which is, so they were looking at two classes of objects, the irreducible unitary representations of fundamental groups of Riemann surfaces and stable vector bundles. So let me just indicate a little bit what do I mean by that. So let pi1 of x be denote the fundamental group or the homotopy classes of paths or loops on Riemann surface X. This group was known to be what is called a Fuchsian group because of it's a Fuchsian group. I'm assuming that the genus of my Riemann surface is at least 2. If it's 1 or 0, then we'll have to state the result differently. So in these cases, this fundamental group was acting on the upper half space, and it's seen as a Fuchsian group, and since it's a subgroup of PSL2R, the automorphisms of the upper half space. And they were interested in irreducible unitary representations of this fundamental group into this unitary group like this. And they were interested in equivalence classes modulo what is called conjugacy or the action of the projective unitary group. So this was the one class of objects they were looking at. And this class of objects had been studied earlier on, as I said, in the paper of Andre Wey. And to each such representation, they could associate. So to rho, they could associate a geometric object, a vector bundle, V rho, on the Riemann surface X. So we are viewing the Riemann surface X as a quotient of the upper half space by the action of the fundamental group. So this is the fundamental group acts freely on the upper half space, and this is the quotient. So you can think of this H as a principal pi1 bundle on the Riemann surface X, and this associated vector bundle is to this rho. You can look at the representation rho. So this group pi1x will be acting on the complex Cn through a unitary representation, and you can look at the vector bundle, which is defined to be H cross rho Cn, which is basically upper half space H cross Cn modulo an equivalence relation, which is through this diagonal action of the representation rho on the upper half space, and on Cn through the representation pi rho of the fundamental group. So this associated vector bundle, this is really can be seen as a vector bundle on the Riemann surface X. Vector bundle means that something which is that you can cover the Riemann surface with small disks, and this vector bundle will be locally trivial on each of those things, and there's a gluing datum. So their idea was these vector bundles belonged. I mean, you can look at the space or the set of vector bundles, but the hard part was to say that the space of vector bundle had some geometric structure. So it was in those days that the notion of stable vector bundles had already been defined by David Mumford in 1960-61. This was Mumford's Geometric Invariant Theory, a book which was, I would say, it started off as a paper and became a book, I believe. Mumford had constructed the so-called modularized space of stable bundles, which means that he could give the set of stable bundles isomorphism classes of stable bundles. Stability is a notion which I don't want to define because it's a general talk, but there's a kind of a slightly smaller class. I mean, you don't want to go into all vector bundles. You are going to restrict your attention to vector bundles of some rank and degree, and stable bundles was a kind of a natural subset there, and Mumford could give it a geometric structure, and this was the moduli space of stable bundles. And as I said, the unitary representations of the fundamental group had been looked at very closely by Andre Weil. And what Narsiman and Seshadri proved was that this association to every row to give this vector bundle V. So you restrict your attention to so-called irreducible unitary representation. Irreducible can be defined as in the classical Schur lemma kind of thing, that, I mean, the image of this acts as a, I mean, the image of this group is a irreducible subgroup of the unitary group here. So it doesn't leave any proper subspaces of CN invariant. That's what it means. So if you put the condition of irreducibility, then the associated vector bundle V rho, which comes out of this association, in fact is stable. And the hard part was that this, which looks like a set theoretic correspondence, had to be proven. I mean, so that it has to be proven that it's an equivalence of categories, and Narsiman Seshadri brings in geometry, and they look at the manifold of this space of irreducible representations. They study the deformations of representations in the earlier paper. Then they look at the space of stable bundles that Mumford had constructed and show that this association has the properties of continuity. They show that this is injective in some sense. The image is open. For this, they use the, I mean, these spaces have the same dimension that can be computed. And then they showed that the image, in fact, is open by using Brewer's theorem on invariance of dimensions. And then they are able to extend this. I mean, some sort of compactness is required, some sort of properness is required. So you want to prove that these two spaces are homeomorphic, which is what they did. Topological homeomorphism is what they established, and thereby the sort of bijection of the isomorphism classes, and hence some sort of an equivalence of categories. So this, I mean, using this fact that this map is continuous, this is open, this is injective, and this is, you can extend it to sort of not just the irreducible representations, to the space of all representations. And the space of all representations, in some sense, is a compactification because the unitary group is compact. And that would, in some sense, force this associated, this morphism rho to V rho to be actually proper, which was one of the crucial parts of this work. And bringing in all these ingredients together, they could set up this bijection. So that was the Narsiman-Seshadri theorem, which became very important in many ways. So there's an analogy, this Rosetta Stone analogy, which I'd like to share with you. This is something which comes up in Andre Weil's lecture to his sister, Simone Weil. So setting up such correspondences were somewhat like the process of building a Rosetta Stone for the deciphering of hieroglyphics. The two classes in the Narsiman-Seshadri theorem were two of the languages on the Rosetta Stone. People should know that the Rosetta Stone was the one which had statements written in 3 different languages, and you have to decipher the third one. The third language came up much later from the work of Simon Donaldson during the mid-80s. Once provided, I mean, Donaldson gave what is called the only differential geometric proof of this Narsiman-Seshadri theorem. Once all the 3 came together, once provided, many subtle and beautiful aspects of differential geometry, topology, mathematical physics, and number theory got miraculously unraveled. And this was in the 90s. Several things happened. I mean, I don't want to get into that. There's a huge body of work, which is, I mean, talking about Donaldson's work on 4 manifolds and Witten's work on Zeiberg-Witten invariance, and so on. I mean, all of them in some sense had their roots in the Narsiman-Seshadri theorem. So I just wanted to say that, I mean, this one could kind of see this Narsiman-Seshadri theorem from the so-called, I will just say that there is a method of continuity. This is a method of proof, which an attempted method by Felix Klein and Poincaré for the uniformization theorem. The uniformization theorem said that, I mean, classifies the simply connected covers of Riemann surfaces. I don't want to go too much into it, but the beautiful thing about this Narsiman-Seshadri theorem is that unconsciously, I mean, or rather at a very subconscious level, they kind of linked themselves to a method which was kind of discarded by Klein and Poincaré. This was looking at representations of Fuchsian groups in SL2R, discrete and faithful representations, and to each representation they could identify some sort of a, I mean, you could look at the space of metrics on oriented, closed, connected surfaces of genus bigger than or equal to 2. And you could look at the space of metrics modulo isotopy equivalence, and that is the Teichmuller space. I mean, all this is a modern perspective. Then to each representation of the Fuchsian group into SL2R up to conjugacy, you can associate a metric in this class, and they were attempting to prove the uniformization theorem by showing that this association is in fact a homeomorphism, which is eventually true. And I mean, it can be proven now, but the ideas were very interesting. And finally, it was the work of Brewer. I mean, Brewer's, there's a correspondence of Brewer with Poincaré where he's suggesting that his ideas are essential towards completion of the argument, which was never done then. But recently there was a volume on Poincaré where this method is there, and Narsiman, in fact, told us about this connection sometime about 10-15 years ago. So now I'll go to Seshadri's other deep contribution, which was in the subject of geometric invariant theory. And this was a classical area, and the invariant theory questions were, studied a lot by Hilbert and several other people. And there was Mumford raised it to some sort of a monument status in his work because he connected it to constructions of spaces. I mean, where invariant theory could be used to construct geometric objects. Mumford's Sichadi approach provided the framework for most moduli space constructions, which came up then, and even to this date, the construction of the so-called core spaces for stacks has its roots in these kind of ideas. There were 3 papers of Seshadri's. The first one was the Unitary bundle paper, which was just after the Narsiman Seshadri paper. This, in the Narsiman Seshadri paper, I was trying to point out that there was this properness business of proving the association. They didn't have a good space of compactifying of the stable moduli space. And so Seshadri then used Mumford's geometric invariant theory to construct a natural compactification of the moduli space of stable bundles, isomorphs and class of stable bundles. And for this, he introduced the notion of S equivalence. The terminology S equivalence comes from the nomenclature given by Narsiman and Raman, S standing for Seshadri, and also could be for semistable equivalence. So this was an equivalence which was some sort of an orbit closure equivalence. I mean, the orbit equivalence in some sense is like isomorphs and classes, but orbit closure equivalence is a more complicated equivalence. And Seshadri's contribution here was to show that that is the natural equivalence which comes when you do geometric invariant theory. So this business of introducing orbit closure equivalences and making, constructing compactifications of stable objects became the prototype for constructing compactifications by GID. So this was, so in some sense, a foundational paper, Seshadri's paper in the Annals of Maths in 1967. The second one was on Mumford's conjecture. Mumford had, I'll come to it soon enough, but just a little later now. Mumford had made conjectures, and Seshadri proved this conjecture as this was Mumford's theory originally was in characteristic 0, and Mumford was setting up the right foundations for doing things in the positive characteristics, because for arithmetic applications and things like that. And Mumford's conjecture was proved by Sichadi for the GL2 case, which itself was quite a beautiful argument. And but the paper had many other things. This was in the so-called 1968 TIFR volume on algebraic geometry, which is I said so-called because it is famous for several very beautiful articles in that. And the Seshadri's paper had, although he proved the conjecture for GL2, he could show that you could in some sense construct these moduli spaces by circumventing many of these ideas, and even in positive characteristics. So this is main contribution of his paper there. And then in the third paper, which came in 1970 in the Annals of Maths, which was on quotient spaces modulo reductive groups, he set up the foundation of studying quotients as algebraic spaces. I mean, this is a work of Kolar and Kiel and Mori, which comes later in 1990s. And Seshadri's several ideas there. He introduced the foundational technique of elimination of finite isotropies, which Kolar uses very non-trivially in his work. And the so-called Seshadri ampleness criterion, and Seshadri constants, which became very famous afterwards, they come up in this paper of Seshadri's. So I'll remark a little bit on this below as we go ahead. So this was Seshadri. In fact, I think this paper came up because Seshadri wanted to give a geometric proof of Mumford's conjecture. And so his philosophy, or at least the original idea of Mumford's conjecture, was the following. So let me just say that, you know, Mumford's conjecture is the following. So Mumford's conjecture. So the notion of some G being a reductive group is classical. I mean, you could think of it as, I mean, I don't want to get into a technical definition of what a reductive group is, but most groups that we know of, I mean, the classical groups and the exceptional groups, they're all reductive groups. And there was a property that Mumford wanted, which he called geometric reductivity, which said that if G is a group which acts linearly on a vector space, finite dimensional vector space V, and if V is a vector, non-zero vector, which is G invariant vector, then the property of what he called geometric reductivity was to say that for every such non-zero invariant G invariant vector, there exists a G invariant homogeneous polynomial, homogeneous F, a polynomial on the vector space V of positive degree, invariant polynomial, such that F of B is non-zero. So this was the property of geometric reductivity. And if people know what is linear reductivity or complete reducibility, which would tell you that if B is an invariant vector, then you can look at the one-dimensional subspace of generated by V, and the property of linear reductivity means that you can get a G invariant complement, a supplement of this one-dimensional vector space V, so that V is a direct sum of these two. And such a supplement would, in some sense, be equivalent to getting hold of a linear function F, which has this property. But for geometric purposes, Mumford wanted a homogeneous polynomial of positive degrees so that this happens, and he called this property geometric reductivity. And in some sense, the philosophy there, as I said, the Mumford-Seshadri theory was that if the group was geometrically reductive, then this quotient, I mean, you could start with the projective variety X on which G is acting, and you can transfer the property of the action of the group on the projective variety into some sort of a linear action on the cone. And if you the quotient, which is equivalence classes of semi-stable points for a linear action of G on a projective variety, the set, if this could be given a structure of a projective scheme, then Mumford's conjecture holds. That means you can prove that reductive is geometrically reductive. So this was some sort of a geometric translation of a very purely algebraic property from reductive equal to geometric reductive into some property of the quotient space having some projective scheme structure. So the basic conjecture was proved by Habush in 1974, but I mean, Seshadri's characteristics were such that he just could not let go of his original thought process and his argument. So I think somewhere around early 2000, he saw that there was a new work of Sean Keel. This was the kind of missing ingredient which he needed to complete this picture. And Seshadri and Pramod Shastri completed Seshadri's old argument. And the new ingredient of Sean Keel was, under some conditions, line bundles, which are so-called numerically effective. And F bundles and big are semi-ample. These are technical terms. I don't want to get into that. So there is a recursive property for Neff line bundles to become semi-ample in Nakai-Moussajon criterion for semi-ampleness, which is the work of Sean Keel. And Seshadri's original thought process, where he was trying to prove Mumford's conjecture using the geometric arguments, gave rise to Seshadri's ampleness criterion in the same spirit. And that's the reason why he was looking for the key ingredient which was missing at that time. And in the Seshadri ampleness criterion, it was a kind of an extension of the Nakai-Mosejon criterion, and a certain constant comes there. And an effective notion of this constant was later on given by Demai, and he gave it the name Seshadri constant. So this is the origin of Seshadri ampleness and Seshadri constants, which came up in this paper on quotient spaces. So the next piece of work that I'd go to is the analog of the Narsiman-Seshadri theorem for a very general class of Fuchsian groups. Fuchsian groups, the fundamental group, as I said, was an example of a Fuchsian group. You could look at more general discrete subgroups of PSL2R, and if you restrict your attention to Fuchsian groups which act with the so-called parabolic or elliptic fixed points on the upper half space, to irreducible or unitary representations of such spaces, you can associate geometric objects exactly like the Narsiman-Seshadri theorem, but these geometric objects will be vector bundles on the Riemann surface with added structures, which are called parabolic structures. So they introduced so-called parabolic bundles, which is a very flourishing industry now. Many scores of papers have been written on it. And much later, sometime as late as 2015, Seshadri and I wrote completed this theory to homomorphisms of Fuchsian groups into semi-simple algebraic groups, which Seshadri always felt, could be done, but when the equipment and the theory was not fully grasped at that time. And so as late as 2015, Seshadri was still active, very keen and with sharp intellect and perfectly comfortable with the most abstract of notions. So now, so I don't know whether I should give a little bit more about. So I just wanted to say that maybe I don't know whether I should give. So the theory was that, as I said, to representations rho, for young people who are looking at this talk. So this rho is, as I said, the representation of a Fuchsian group into the unitary group, and this is, I'm talking about the Mehta-Seshadri theorem. So this gamma is going to act on the upper half space with a finite set of points which we can assume to be so-called elliptic fixed points or parabolic fixed points. It just depends on what sort of stabilizer subgroups gamma has at these points. And if you look at this gamma will not act freely now. It will act with isotropies. So you can look at the quotient map from H to H mod gamma, which is your Riemann surface X. And you can, in some sense, make this association V to V rho by a process using this map P. And to rho, we can associate this vector bundle V rho now, again on X. But this V rho is not just a vector bundle. It's a holomorphic vector bundle with, if you look at the image of these points, A1, A2, AM, and there's some X1, X2, XM here. And this is orbits here. They're not just points. So if you look at these corresponding images of these points here, this vector bundle V rho, depending on this representation, will have flags at these points, and they come with some weights. So the idea of Mehta and Seshadri was to have a notion of a new notion of stability for these objects, which was the parabolic stability. Many of these, some of these ideas, at least in the case of elliptic fixed points, goes back to an early paper of Seshadri in a Verona conference in the late 1960s. He was already looking at these questions, but he always told me that he just could not push the whole idea because he didn't have a full proof of the properness of the moduli space of what he called pi bundles. He had a proof there, and but he wanted a proof which was avoiding some sort of coverings which was being used by Seshadri then. And it was the joint paper of Mehta and Sichadi that some sort of evaluative criterion was used to prove the properness, and that's how the paper got completed. This was almost, I think it was in 1980, and this is a famous paper of Mehta and Seshadri. So this was, I didn't spare, this was the, Seshadri had done several other pieces of work. I mean, there's a whole, there's a volume in the Asterisk series called the Fibre Vectorial, it's in French. And the notes were taken by Jean-Marc Drezé. And this collection has lots of, I mean, there are several results of Seshadri on desingularization, and Seshadri's, one of his favorite themes was understanding degeneration of moduli of vector bundles when the curve degenerates to a nodal curve. So he was interested in vector bundles on singular curves also, and these questions were coming from compactifications of Picard variety. There was a famous paper of Seshadri's, which I have not mentioned here, which is the so-called Oda Seshadri paper, which studies the compactifications of the modulus of the Picard variety. And here I can tell you that Seshadri kept telling me that, you know, he was in Harvard in those days. Oda was also there, and David Mumford was looking at these questions. There was a paper of Meyer and Mumford which was looking at the question of compactifications of Picard. And when Seshadri was there, Mumford asked Seshadri whether Seshadri told him that maybe one could use GIT. He was telling Mumford this, and Mumford asked Seshadri whether Seshadri could solve the question using GIT for the dollar curve, a singular curve like this. And I believe that, I mean, Seshadri told me that basically Seshadri made the computation for this case, which showed that even for the rank 1 case, that is the Picard case, the notion of semi-stability plays an important role, and which was a kind of new thing, because in the rank 1 case, semi-stability was not visible for the usual construction of Jacobian and things like that. So Seshadri's view, a point of view was that if you look at something like a reducible stable curve, this is an example of what is called a stable curve. And Seshadri then gave numerical criteria as to what should be the objects in the boundary of the Picard, which gave the idea of a compactification. And then this was developed in a very big way by Oda and Seshadri in a 90-page paper in the Transactions. So this is the construction of the compactification. So Seshadri was always fond of singular objects, singular curves. And then there is towards the end of 90s, Seshadri, Nagaraj and Seshadri, they did highly non-trivial work on degenerations of moduli space of vector bundles when the limiting bundle curve was a stable curve, which is an irreducible nodal curve. And this is highly referred to work now, which has developed a lot. So this was Seshadri's theory of using torsion-free sheaves, and so, I mean, those ideas were used here. So I don't want to go too much into this. I just wanted to say that there's a whole body of work which Seshadri did. Then he also studied the desingularization, where subsequently I was also involved in a little bit. So I just want to quickly come to his second half of the other half of his. I mean, he broadly worked on two different areas: the moduli theory, algebraic geometry, and invariant theory. On the other side, he worked on representations of algebraic groups, and this was from early 70s. So Seshadri wrote a paper in the mid 70s. I think his student Lakshmibai had joined him in the late 60s. Musli had joined him in the late 60s, and then Lakshmibai. And Seshadri, Lakshmibai, and Musli, they got together, and they were. Seshadri had this idea of generalization, a vast generalization of the classical theory of Hodge for Grassmannians. And the idea was construction of bases for the space of sections of line bundles on Grassmannians, which was done by Hodge, but later Seshadri wanted to generalize it for more general Schubert varieties. Schubert varieties had the added Weil group element. So the aim was to construct such natural basis which reflects the intrinsic geometry of the Schubert variety. And also intricate combinatorics of the Weil group comes into the picture here. And Seshadri and Musli, Seshadri and Lakshmibai wrote several papers, which all appeared in the Indian Journal, but they were foundational papers referred to by several people. And this was the so-called geometry of G mod P. This was the series of papers. Geometry of G mod P. I mean, this was the title. It starts with 1, and I think it goes all the way to 9, I think. Sometimes Seshadri with Lakshmibai, sometimes all three of them together. But it was a huge piece of work. And this theory has led to fundamental developments in the field of representation theory, geometry, and combinatorics. So there's a lot of technicality here, and it's not going to be easy to talk about that. So following this series of this, at this time when Lakshmibai and Seshadri were working, they were making very careful analysis of these issues and on the basis, especially when they're looking at Schubert varieties for exceptional groups. And Lakshmibai and Seshadri formulated the so-called LS conjectures. They didn't give this name. It was given much later by Peter Littleman. So this is the Lakshmibai-Seshadri conjectures. They were very beautiful combinatorial conjectures. And the key point of these conjectures was that it gave some sort of an indexing to this standard monomial theoretic basis, which this is not just giving some indexing. This indexing which implied a remarkable character formula, which is now called the LS character formula. And these were some sort of conjectures, and the character formula was natural consequence of those conjectures. And sometime in the mid-90s, and there was this. So these spaces that we're looking at, the space of sections of line bundles, they got connected to the so-called de Mazur modules of the Schubert varieties, and Littleman proved these conjectures by bringing fresh inputs and new ideas from the theory of quantum groups. And I must mention that there's some very nice paper by Raghavan and Parmeshwaran, which carried on this combinatorics and this thing to give a new kind of basis for these objects. I don't want to talk too much about the technicalities here. So Peter Littleman solved this conjectures, and it was again very fundamental breakthrough in this whole thing. So this is a very brief story about Seshadri's work. I didn't want to go. Seshadri's other passion was the creation of Chennai Mathematical Institute, and the Chennai Mathematical Institute was founded in 1989 in times of crisis. Chennai Mathematical Institute came up. Seshadri had joined math science in 1984, and in the 5 years of Seshadri's stay at math science, there were several issues there, and then Seshadri was asked to start the SPIC Mathematical Institute by A.C. Mutaya in 1989. Seshadri took the plunge, and then later on this institute was called the Chennai Mathematical Institute. In the first 9 years, it was a research institute. And around 1998, because of funding crisis, Seshadri had a brilliant idea of making this into a different kind of an undergraduate institution, which was run by researchers. He was modeling it after what he thought was the École Normale Supérieure model, or the model of some of the top American universities. That was his vision for the place. But I remember much before this crisis, in the early 90s, in one of his moments when he was reminiscing about things, he pulled out a letter from his drawer and showed it to me, a letter written to A.C. Mutaya. This was even in early 90s, where he had said that eventually that the institute should become a top-class undergraduate institution run by people who are doing frontline research. This was his guiding principle there. And so in some sense, the financial crisis gave him the opportunity to give shape to his dream. So he used it immediately and started this undergraduate CMI undergraduate program, which has everybody knows, and it has been mentioned a lot now, has come a long way in from those days through several periods of crises. Anyway, so I just wanted to, so CMI was Seshadri's, apart from algebraic geometry and Schubert varieties, CMI was his something which engaged him very intensely for the last 30 years of his life. So a few words about Seshadri's personality. So Seshadri as a person. So I have known Seshadri as his doctoral student since 1984. I joined Seshadri 3 months after he joined the Math Science in November 1984. And I've then later on I became his collaborator and colleague at the Chennai Mathematical Institute. And I've had the pleasure and privilege of witnessing his personality, mathematical personality, the manner in which he thinks, which is rather unique. In fact, a mention of the manner in which he does algebraic geometry, it comes up in Caroline Parek's biography of Zariski. Zariski saw Seshadri's non-canonical way of thinking, and I was fortunate to have some sort of I could get into the wavelength of Seshadri's hidden statements, and they made my own career. So as a mathematical personality, I saw someone unique in his vision and insight, an uncanny ability to consistently strike gold in a vast world of mathematics. That means in some sense, if Seshadri felt that something was interesting, then one could be sure that there was something very deep hidden there. In a volume of tribute volume of when Seshadri turned 70, Arun Ram has something very nice to say. I don't remember now. He said that if Seshadri found something interesting, you can be sure that it's worthwhile pursuing. So this is Seshadri's uncanny ability to strike gold. Just thinking of wherever he saw something, it meant that there must be something deep there. He was extraordinarily generous with his ideas, and he shared his insights with one and all. And this extreme generosity was his human side as well. So both in personal life, both he and his wife Sundari, they were extraordinarily generous people. And Seshadri was like an open book. Always, of course, the caveat was that the listener go back and pursue the ideas to the best of their abilities. And there used to be this constant pressure. There was this famous, whenever Seshadri, after Seshadri has shared some of his ideas with anybody, then the subsequent meetings will always be a phrase which says anything, which means he will ask this question in a very anything, and that meant has anything come out of those ideas? Has there been work on it? As a person who's been listening, has he been just sitting idle, or has he been doing something about it? This was one single word which carried everything in it. And it was simultaneously an enthusiastic anything, but it was a huge pressure on the person who was listening to it. So this is Seshadri's subtle way of applying pressure on the people who are recipients of his ideas. And so this was his way of sort of continuing his, the work has to be continued. So that's the way he looked at it. And it was very challenging. And there was and Seshadri he was completely aware of his own stature. And because he was so completely aware of his own stature, he was naturally absolutely modest. He didn't have any insecurities at all. He knew about what he was. And at the same time, he was absolutely humble, very simple, almost bordering on naivety. He was a simple, naive person who didn't know many things about normal human things. So it was a very unique combination of a rather special mathematical brain, which was high in stature, and a very modest and humble personality, which was visible for all other interactions. He was also in leadership. Nobody would have, if people had seen his personality earlier in math science, leadership in the sense of directing an institute and things like that would not have been easy to attribute to somebody like Seshadri, but Seshadri proved everybody wrong. I mean, he had insights, and he was very confident of his insights. What he felt was his intuitions about how things should be developed, and this confidence made him very calm. He was unperturbed during several moments of crisis that the institute faced, even during the math science times or later on at CMI, when CMI perpetually faced financial crisis. Seshadri was always unperturbed, and he was always dynamic as to find out what is the next thing to be done to carry on the activity. The work must go on. And Seshadri had a unique sense of humor and sympathy. He could meet anybody on the corridor and he would ask them about their welfare and things like that. And his sense of humor was infectious. His smile was remarkably infectious. I mean, anybody could joke with him and they will be having a very good time. And this was the hallmark of his personality. His interests were ranging widely from mathematics, philosophy, politics, and music. And music was a passion of Seshadri, which started very early in his life. I think he learned his basic music from his grandmother. That's what he told me. And this was, in some sense, his style of singing was somewhere close to. I mean, I would be rash in saying this, but something like Brinda Mukta's brand of Carnatic music. I think, interacted with Rangaramanuja Iyengar in Bombay. That's what he told me. Most of the compositions that he used to sing were self-taught. And this was again a remarkable trait of Seshadri's. And Seshadri was, I would call him a real expert in Dikshidhar and Shyama Shastri Kritis. He used to be a regular singer on the Saraswati Puja days at CMI. And it was the memorable moments of CMI was his singing in the library. And this was a tradition that he followed for 30 years. I mean, from 1989. And Seshadri's grasp of the nuances of Carnatic music, he could have been, he kept to himself, he was never a performer. And he kept to himself as a singer, never really went too much into it. But people who have heard him in private know that he was top ranking. I think he ranked very well in music, as high as he ranked in mathematics, in my opinion. That's my opinion. Anyway, I'll finally quote Professor K. Chandrasekharan, who in a letter to Seshadri on the 10th of February 2013, he wrote, "I cherish the values that inspired the creation of CMI and your unswerving commitment to those values." So I would say that Seshadri will be remembered for these values that he brought in, and in his mathematics, impeccable high standards, quality, and also integrity, and in mathematics in the institute building of CMI, all these things came in as foundational things, and one just hopes that CMI will develop and live up to the standards that he expected it to live up. So I close with lines from Auden. This is the hymn to the United Nations. This is so, like music, when begotten notes, new notes beget, making the flowing of time a growing. It is what it could be when even sadness is a form of gladness. So with that, I'll close this talk. Thank you.
Thank you, Professor Balaji, for this extraordinary talk. And we have basically some questions.
Sure.
Yeah, so these questions came from YouTube. You can also see those in your chat box, but I'll read it out for you.
That'll be better, yeah.
So I heard that Donaldson gave another proof of Narsiman Seshadri theorem. Was it completely new or inspired by their work?
It was completely new. This was a differential geometric approach. one of the important things about the old proof of Narsiman Sichadi, as I said, is a kind of a strange density argument. You set up this map and you prove that the image is open and closed, and then you prove that it is the whole space. There was not a, whereas in Donaldson's argument, there was some sort of a constructing, I mean, it was not the representation that he constructed, but there was some sort of an Einstein-Hermitian connection that he could construct on the bundles, which gave a grasp on some sort of a, it was a very different in spirit and flavor. Yeah.
Okay. Yeah, and the next question is, how does Remembrance theorem come into action of the Narsiman-Seshadri theorem, and how was the great influence of Grothendieck on Seshadri and other generation of mathematicians who entered the temple of algebraic geometry in 1960s? Yeah.
So the Remembrance theorem really is too basic. I mean, it had influence in everything that happened in algebraic geometry. It was almost like a large philosophy of, I mean, which linked topology of and algebraic geometry in a big equality, which is the Remembrance statement. So it didn't have any specific impact on the Narsiman Seshadri, except that everything was, I mean, Remembrance theorem was like almost alphabets in if you want to do algebraic geometry. But Grothendieck's influence, I must say that I have to say that Seshadri was the first person who brought scheme theory to India. I mean, algebraic geometry of language of schemes. It was a bold thing. I mean, he came back in the 60 and I think started giving courses and introduced scheme theory in a very big way. I think even Narsiman and Seshadri both were there during those times. Narsiman's slant in those days was more analytic, but I think he was also very, very much influenced by Grothendieck's point of view. So both Narsiman and Seshadri, when they came to TIFR, they brought modern algebraic geometry in this big way. It was taken up immediately by several people at that time. Seshadri had a galaxy of people who were, I mean, Seshadri's students were Pauman Murthy, I don't know, C.P. Ramanujam, whether he was, I can't be called Seshadri's student, but he was also one of the people who was highly influenced by Seshadri's thought process. And I mean, at that time, Raghunathan was there, and Ramanan was, these people were with Narsiman, and they were also top graded algebraic, I mean, they knew algebraic geometry, the scheme theory at the front level, and then Raghavan Narsiman was there who was doing analytic geometry. So it was algebraic geometry was, it was infectious in some sense and influenced everybody. And in late 1960s, TIFR was one of the world centers of algebraic geometry, and they had this huge conference where Grothendieck came and spoke about his so-called standard conjectures in 1968. And so I guess the influence of algebraic geometry was viewing this kind of Rosetta Stone kind of picture. You know, I mean, although this statement is from Andre Wey, trying to see analogies, trying to see symmetries, looking at groups. I mean, trying to understand whether objects generate groups in some sort of what I call Tanaka categories. I mean, all these things were a kind of almost natural thought process that people imbibed. And it became so natural that people now cannot even think without all that. That's the kind of influence that Grothendieck had, and Seshadri imbibed it completely and brought it into India. I would say he introduced Grothendieck's algebraic geometry to India, and today it flourishes because of him.
Okay, and one more question came from Snehojit Misra, who said that, is there any contribution of Seshadri in Falting's approach in moduli of bundles without using GIT?
Yes, the paper of Falting's was written. This is a technical question because somewhere in Falting's construction, where theta functions are being used, it is without GIT, but GIT does play a role. I mean, it is influencing the thought. It is telling you what to choose to construct as your invariants. I mean, looking at theta functions was the way in which Jacobian was constructed. So Falting's idea was to look at the same sort of theta function idea for construction of vector models. But what he could construct was some space whose normalization was the actual moduli space. And some ideas were required there. I think I remember that when the paper was written, we ran a seminar at CMI, and Seshadri wrote to Faltings about, slightly different more approaches. And Seshadri kind of rewrote parts of Faltings by trying to see it from the standpoint of GIT. So although GIT doesn't directly come in, it is somewhere there as the background. I won't say it is, you can, it's not prominently there, but it is there.
I would like to read what I wrote to the faculty of IIT Bombay. Just one
Please,
moment.
Please.
As soon as I got the news, next day I wrote something for the IIT Bombay faculty. So I would like to simply read that.
Sure.
Yeah, just one moment. So this I posted on 19 July. Yeah, this is a copy of my post to faculty of IIT Bombay. So I'll just read this. There is some noise coming.
Maybe I should.
Yeah, hello. So can you hear me?
Yes, we can hear you, sir.
Okay. We have lost a mathematician who had many other talents, such as accomplished classical music singer and a top administrator. His mathematics was of highest quality. It combined geometric insight with mastery over whatever mathematical tools were needed to solve the problems of contemporary interest. He could connect very easily to people of all ages. He was eager to discuss mathematics anytime with anyone. He remained active in research and music until the end. He built an institute in a PPP model that was unheard of in those days. His aim was to attract the best undergraduate students to take up careers in academics. For many decades, education at CMI was almost free, although it was in PPP model. It attracted top mathematicians from around the world. This was due to the stature of Professor Seshadri. Whenever I met Professor Seshadri, at first at the Speak Science Foundation in T Nagar, and later at the Chennai Math Institute, he would welcome me with a big smile and talk about whatever mathematics I was pursuing. And whenever I met him, I found him surrounded by many people who were eager to talk to him. And when I first saw the Chennai Math Institute and the statue of Lord Buddha, I could feel the sentiments that he had while building this institute. It's a unique experiment. It is extremely successful. And I'm sure that this will be his lasting legacy besides his beautiful mathematics. His philosophy in running the institute was very simple. This is what I could perceive. Attract the best faculty, best students, and offer very demanding courses. Students of BSc at CMI usually know whatever we teach at MSc and even PhD level in universities. And it was no wonder that so many of them have gone on to the best graduate school, and some of them are faculty in the best places in the world. Seshadri solved cells conjecture in dimension 2, which was a major problem in commutative algebra. He was still a graduate student at that time. This work inspired several generations of mathematicians, as Balaji mentioned, that Pauman Murthy took this problem and it started a whole generation of research work by students, and it continues. But Seshadri's real love was algebraic geometry, a subject which is much more demanding, but well connected with all fields of mathematics. While he was at TIFR, the School of Mathematics at TIFR became a leading center of research in the world in algebraic geometry, and it was due to his courses, his inspiration, and his training at TIFR. Seshadri constants are now active areas of research in algebraic geometry, and as Balaji mentioned, there are many other areas which Seshadri has more or less created from scratch, which have enriched algebraic geometry. He was of course, the awards were mentioned that he was a recipient of Bhatnagar Award and FRS and Padma Bhushan. And for a man of that stature, these awards did not mean anything. He remained humble human being throughout his life, and we will miss him greatly. Thank you.
Thank you,
Thank you.
sir, for your excellent words.